So we've learned a little bit of Scala. Let's talk about Spark, and then we'll start to put it all together. So at a high level, what's Spark all about? Well, if you go to the Spark website, it describes itself as a fast and general engine for large-scale data processing. And well, that's pretty much what Spark does. It is basically a framework that you can use for programming the distributed processing of large data sets. So it contains functions that let you import data from a distributed data store like an HDFS file system or S3 or something like that. And it provides a mechanism for very simply and very efficiently processing that data. So, assigning functions that transform that data or perform various actions upon it. And it can do this on a cluster using the same code that you use to run it on your own desktop. So the same code can be run on your own desktop for development purposes, as well as on a real cluster of computers that can be scaled out as large as you want. So the whole power of horizontal scaling is available to you, where if you have a massive data processing job, all you need to do is throw more hardware at it until you can actually handle the whole thing. So that's kind of the whole idea behind Spark. It lets you do things you could never do on a single computer. And it is highly scalable. So the high-level architecture of Spark kind of looks like this. So basically you develop a driver program. So all the scripts that we're going to be writing in this course are driver programs. And they are built around one object called Spark Context that sort of encapsulates the actual underlying hardware that you're running on. Now, on top of that, you are running some sort of a cluster manager, and there's one provided by Spark, or you can actually use it on top of a Hadoop cluster if you want, and use Hadoop Yarn as well. Also, Apache Mesos is an option too. And that cluster manager is then in turn responsible for distributing the work defined by your driver script among multiple nodes. So every node that you run on, every machine, might have an executor process, which has its own cache and its own list of tasks, and it can split that data up to multiple executors. So if you have a massive data set, it might take one little chunk of it and put one chunk on each one of those different nodes on your cluster for parallel processing. And then your cluster manager figures out how to recombine all that data and pass it on to the next step if necessary. But the beautiful thing is that all this stuff on the right here just happens automagically for the most part. All you really concern yourself with as a Spark programmer is primarily the logic about how you're going to process this data. Spark and the cluster manager are then responsible for figuring out how do I distribute it in an efficient manner. Now, that's not to say you're totally off the hook for thinking about how it gets distributed, and we'll talk about tweaking these things later on, but for the most part, it just works. Why use Spark as opposed to something else? Well, a lot of people compare it to Hadoop MapReduce, and MapReduce was kind of the first technology that came out for doing distributed processing of data on a cluster. And Spark claims to run up to 100 times faster than MapReduce if you're running in memory, or 10x faster on disk. It is pretty fast. I mean, your mileage may vary, of course, and these are sort of best case scenarios, but Spark is generally preferred over MapReduce for that reason. It is generally a faster thing, and it's more modern, has a little bit more capabilities to it. In MapReduce, you'll find yourself writing a lot of things from scratch and kind of like wrapping your head around how to fit a problem into the MapReduce coding paradigm, whereas in Spark, it's generally a lot easier. The reason that it's so much faster is that Spark uses something called a directed acyclic graph, a DAG engine, to optimize its workflows. So one thing that's kind of neat about Spark is that nothing actually happens until you actually hit a command that says, I want to collect the results and do something with them. And once Spark sees an action like that, it will go back and figure out the optimal way to combine all of your previous code together and come up with a plan that's optimal for actually producing the end result that you want. So it's a very different paradigm than how MapReduce code works, for example. And that's kind of the secret to its efficiency. A lot of people are using Spark in the wild, and I'm sure there's many more than just this list right now. There's a little website here at the bottom here you can look at if you want to see the latest list, and I'm sure a lot of big companies just aren't telling people how they're doing stuff internally. There's a lot of secrecy in the corporate world. But people who have fessed up include Amazon, eBay, NASA, TripAdvisor, Yahoo, and many, many others. I'm sure it's also used very widely in the financial industry as well. And pretty much anyone that has big data, I'm sure, is doing something with Spark these days. It's not really that hard. I mean, I think you'll be surprised at just how small these Spark driver scripts are that we're going to write. It's a very powerful language and a very concise language that we're going to be dealing with. And you can code in Python, Java, or Scala. Again, I'm recommending Scala because it's going to give you the most efficiency and probably the tightest code for dealing with Spark programs. But if you do want to stick with Java or Python, that's also an option. And Spark is really just based around one main concept, the resilient distributed data set. And this is basically an abstraction over a giant set of data. And you just take these RDDs and you transform them, and you perform actions on them. And that's really all there is to programming in Spark. It's just a matter of trying to figure out the right strategy of how to get from point A to point B, where you have a set of input data and a desired set of results. But the actual code in between is generally surprisingly simple. Now, Spark itself consists of many components. So Spark Core kind of deals with the basics of dealing with RDDs and transforming them and collecting their results and tallying them and reducing things together. But there's also some libraries built on top of Spark to make some more complex operations even simpler. So one thing is Spark Streaming. That's actually a technology built on top of Spark that can handle little microbursts of data as they come in real time. So you can process a stream of data from a fleet of web servers, for example, or maybe a ton of sensors from an Internet of Things application as they come in 1 second at a time, and just keep updating your results as you go in real time. It just runs forever. Pretty cool stuff. Spark SQL allows a SQL-like interface to Spark, and you can even open up a little thing that looks like a database connection to Spark. So you can actually be using Spark SQL to run SQL-like queries on massively distributed data sets that you've processed using Spark, which is a pretty powerful thing sometimes. MLlib lets you do machine learning operations on massive data sets. It's a little bit limited in what it can do today, but it's always getting better. So if you need to do things like a linear regression or even recommend items based on user behavior, MLlib has built-in routines to do that automatically and distribute that across a cluster so you can deal with truly massive data sets and perform machine learning on them in a very efficient manner. Finally, GraphX. We're not talking about the types of graphs that you see, in slide presentations where, revenue's going up and to the right or whatever. This is about graph theory, graph networks, right? So think about like, say, a social network where we have a bunch of individuals connected to each other in various ways. That's the kind of graph GraphX is talking about. And it provides a framework for getting information about the attributes and properties of that graph, and also a generalized mechanism called Pregel that we'll look at later in the course that will let you do pretty much anything you want to that graph in a very efficient and, again, distributed manner. So you could even throw it at, say, a massive social network data set and wrangle that into whatever information you need. So all more ways in that Spark is a very powerful technology. So why are we using Scala? It's probably not a language you know, and asking you to learn a new language is kind of a tall order, I realize. But again, Spark itself is written in Scala. So if you want to take advantage of the latest and greatest Spark features, Scala is the best choice. It's going to give you the best performance, and it's going to give you the best reliability. And it's also going to be the simplest code to look at when you're at the end of the day. There's not a whole lot of boilerplate that we need to add on to Scala code in Spark to get it to work. So it's very simple to work with once you know the basics. But it's really not as hard as you think. Another good thing is that if you have done Spark programming before in Python, you'll find that Scala code looks a lot like Python code in the context of a Spark job. So, look at these two examples here that do the same exact thing in Python and Scala. The syntax is slightly different. We have val qualifiers, whereas, in Python you don't need to declare that. And, we're using a list structure here, and the format for Lambda functions is slightly different, but by and large, it's going to look very familiar. So if you have done some Spark programming in the past with Python, going to Scala is not going to be too much of a leap, actually.